This is the very important and in some sense conclusive part of the topic that we have developed so far. To give you an idea, in the other parts of the talk, we have systematically developed the influence of the different frames, the influence of the low range transformation between different frames, where the observer's frame of reference and the emitter's frame of reference differ from each other's description by addition of a vector quantity that can be that can be boost or some rotation or a combination of the two. And next what we did was bringing out the importance of the wave propagation for different kinds of media. Thus, those frequencies, those propagate easily in a medium at some temperature, are not so when the temperature is raised. So, to give you an example, radio waves can easily pass through a cold plasma, but if the temperature of the plasma is raised, particularly raised close to the pair production energy, these waves are not going to pass through the plasma. There is a natural shield. However, the shield allows its own waves to propagate, but the ones those want to pass through it in the form of a radio wave or something like that, they are chopped off. So, these two that we have discussed so far. So, the next thing that is left is how does the thing that we just discussed as third electromagnetic constant, or the sort of interaction that generates something similar to that, actually assumes the form that can affect the propagation or rotation of plane of polarization and things like those. So, to begin, I start with this loop diagram, and we assume that we are considering a loop such that there are soft photon insertions, and we are interested in situations when the soft photon insertions are odd in number, and we keep summing up the contribution starting from first soft insertion to third soft to fifth soft, etc., in a finite density medium. And when this sum of the all terms of the series is taken into account, one arrives at the expression for the polarization tensor in a magnetic field that is exact to all odd orders in EB and chemical potential. Retaining the term that is first, and it has one power of magnetic field and any power of chemical potential such that these two products are even, is what usually called the term responsible for Faraday rotation. It is linear in magnitude. The associated form factor or the structure of the polarization tensor for such a case is defined as pi p of mu nu. It has a structure that is given by equation 3. The Lorentz structure here what we have is not the same that we had encountered in other situations. It has its Bose symmetry intact, it has its hermiticity properties intact, and not to talk about the word identities satisfaction. It may not be very out of place to share with you that when one evaluates this diagram in this soft limit, it is not that one automatically gets this term that we are showing by equation number 3. There are also some additional terms those appear, and those additional terms on the face of it or as they appear are not 0. We call them additional term because the fact that they do not satisfy the criteria that we have defined, the right criteria to be a part of the polarization tensor. So, these additional terms where they fail is to satisfy the condition that we call here the word identity. So, one has to do some extra calculation and very technical manipulations to show that those pieces actually does not contribute, they are vanishing under all conditions, and then what one is left with is what we have shown here in question number 3. You might be worried that how does this particular part behave in the infrared limit when k goes to 0, because k dot u square means omega square, there is a omega square divided by k square, omega square minus k square, that is coming from 4 k square. So, omega square here cancels, you are left with 1 over square root of k square, which is 3 vector k. Under k going to 0, this term would certainly blow up. So, is the theory that we are considering has a singularity that is coming from the infrared sector? The answer is actually not really, it is not so, because the presence of this u over here ensures that the other spatial parts should take the value which is 1, 2, 3, and in the limit k tends to 0, there is a k on the numerator and there is a k on the denominator. So, both these two quantities should go to 0 in some limit, in that particular limit, and apart from that this pi of k should not have a very bad infrared behavior, and at the end of the day this pi p that we have estimated in the non-relativistic limit assumes the form that I have given in 4, where omega b is the Larmor frequency given by, or scleron frequency given by E b by mass of the electron, and omega p is the plasma frequency square. So, having introduced this, as we already have mentioned, the 3 degrees of propagation yields 1 degree of propagation which is longitudinal and decoupled, and the other 2 degrees of freedom are the coupled degrees of freedom, and with third electromagnetic constant's presence, we can effectively describe the whole system by these 2 equations, and that takes the form which is given by equation number 8, which is a when there is a Hermitian matrix multiplied by the column vector of the 2 propagating degrees of freedom. The result is emergence of 2 modes of propagation with different dispersion relations. Those are given by equation 11 and equation 12, and the quantity that we have defined by A is a contribution that is following from the third electromagnetic constant pi p, and rest of it are already known to you. And physically, in a situation like this, what happens is, if there is a region in space where there is a magnetic field coexisting with a fluid that is charged, then as the wave enters this region, and if it is plane polarized, its plane of polarization undergoes rotation. The rotation we have shown here by a red arrow from the original one, and its angle psi, and psi is the angle that it assumes with respect to its original direction upon emergence from the region where there is this magnetized plasma existing. So, leaving us to deduce the condition that if the length is L and if psi is the angle, then the rotation angle per unit length of propagation is can be now told as d psi by d L, and that is usually the Faraday rotation. The angle of rotation per unit length, it is provided by the difference between the 2 k vectors that is coming from the dispersion relation, wave vectors. What are these 2 wave vectors? They are the normalized eigenmodes, and they are given by A parallel plus I A perpendicular upon square root of 2, and A parallel minus I A perpendicular upon square root of 2. These are the 2. And what is the difference between the wave vectors that we are talking about that follows from the dispersion relation? It is essentially given by this particular relation. Now, provided A is small, that means the magnetic field is small. So, this contribution can be taken to be less than 1, and this can be expanded in a binomial series. Then you just can say that this k plus and k minus is given by this multiplied by this quantity, where inside we have just a factor of half sitting over here. So, what are the limits that this particular or limiting values that this particular estimate can take? the limiting values are dependent on the kind of medium that one is talking about. The medium's temperature or chemical potential can be much less than the other parameters like mass of the charged particles present in the system or the magnetic field, or they are close to the mass of the charged particle, or there are much greater than the same. It is usually believed that if we are in the intergalactic region, it is the first situation that one encounters. If we go inside a hot star, maybe it is the second situation that we will encounter. And if we go to the early universe, before there was a decoupling between the photon and material medium, it was the third situation that was prevalent. So, those are the three situations possible in practice. In the first situation, plasma frequency is given by E square, there should be a square here in omega p. So, it is given by number density of electrons and divided by mass of the electron. So, the dimensionality of right hand side and the dimensionality of left hand side, where the vanishing square is taken into account, they match. And if it is a classical system, the number of antiparticles can be neglected. So, it gives you omega p square equal to essentially n e upon m e, and e square mandatory to give the right dimension, and this is the expression. And that situation for Faraday rotation per unit length. The next possible interesting situation is that of a degenerate background. A degenerate means the temperature can be neglected, the energy of the fermions E f is basically equated with the chemical potential and is related to the Fermi momentum and the mass of the electron by the first relation. When P f is much larger than mass of the electrons, in that situation that we are talking about, omega p square, that is the plasma frequency, can be thought of given by the expression that we have here. This is not necessarily that we have to consider the system to be almost massless. E f can still have mass, but in the degenerate background, it is not ultra degenerate. In the degenerate background, the rotation per unit length is given by this expression. So, omega p square as it is, it stands over here, plus some correction factor that emerges, which is retained on the right hand side, and this total thing is what gives us the rotation per unit length. Okay. Now, depending on, if we take or if you compare these two situations, classical and the degenerate background, we easily see that the difference that has emerged, and that is very distinct difference has emerged, where clearly the classical part is standing apart over here. Similarly, if you go to a ultra relativistic background, now you can see that in the plasma frequency case expression the mass is not there. So, in this particular situation, the Faraday rotation is not only proportional to the magnetic field, it is also proportional to the chemical potential and temperature and chemical potential square coming in this form. Now, if we consider beta to be inversely proportional to temperature, you can see that omega p is basically proportional to temperature and chemical potential square and the square root of that. If we replace it over here in the denominator and we keep increasing the values of the temperature and chemical potential, you might encounter a situation when the denominator will slowly approach 0. This may be a very synthetic situation, because this situation under consideration has been achieved by taking lot of simplifying assumptions. Nonetheless, it reflects a situation when the amount of rotation, Faraday rotation, can be rather large. So, to draw some sort of a conclusion, I think it will not be unfair to say that the rotation of the plane of polarization that one usually finds in the case of Faraday rotation can differ drastically from one situation to the other, particularly when the situations are different in terms of their corresponding magnitude in temperature, chemical potential and magnetic field strength. Okay. So, when one is trying to draw a conclusion about the nature of the emitter and the constituents of the emitter, one needs to do a parallel investigation or take parallel measurements that proves the inference about the medium that is under consideration, and finally, the consistency check can be established. So, with this we would draw the conclusion, and in the concluding section we have 3 observations. The 3 observations are the origin of modification of the propagation modes, their frame dependent effects, orientation dependent effects between frames, and the composition of the media, that effect. We have already discussed that some of these effects can be marginalized by taking appropriate measure like ratios, ratio test, etc., but not all and not everywhere. Therefore, an approach towards consistency of all these measurements and calculations should be kept in mind while interpreting the observational data. Thank you.